Hi everyone, so a few people seem to be struggling with the Matrix lab this afternoon, so I thought that I'd just make a quick video to discuss some of the things that people were struggling with. So the first thing I want to talk about is just the way the constructor worked and the layout of the memory that we used. So basically what happened is that we had a matrix object, alright? This class for matrix had 3 items in it. There was the int star data, there was the int num rows, and there was int num cols. When we called the constructor to create a new matrix, so we would have had code that looked something like this, MyMatrix, and then we would give it the number of rows and the number of columns. If we had code that looked like that, the constructor would be called, and the constructor I gave you automatically allocated everything. So in this case, it would have set the value for num rows equal to 5. It would have set the value for num cols equal to 3. And then after that, it would have allocated all the necessary memory that it needed in order to store the numbers. So in this case, what it would have done is it would have allocated an array of integer pointers 3, 4, 2, 3, 4, 5. So there would have been 5 rows, and then each of these cells stores a pointer. So on line 15 of the code, we see that we allocate this. This then gets set to point to a new array. Likewise for the second line, the third line, the fourth one, whoops, fourth one, and the fifth one. So that's the general layout of how things looked once everything had been allocated. In contrast, when we were talking about the destructor, the destructor would first loop over all of these items and delete them. And then once those were deleted, it would delete the actual data array like that. All right. Once everything was allocated and set up, the data pointer is set to point to that array like that. So we can access an individual number. So if we want to access, let's say the number at 0, 0, we would simply be able to go data at 0, which gets us to here. And then once we're there, we need to follow that pointer across to get to that item, number 0 as well. If I wanted to get to item, let's say we were getting to the item over here, that's in row 0, 1, 2, 3, 4. So it will be at data 4 and column 0, 1, 2. And we can simply access it like that. Remember that under the hood, the compiler is simply doing the pointer arithmetic that we spoke about. So that will look like this, data plus 4, which will then get us down to that pointer there. And once we're there, we then say that amount dereferenced plus 0, 1, 2 dereferenced. One of the other functions that we looked at was the swap function. Now, the swap function said take in a matrix and swap its data with ours. So once again, if we look at our layout, we can have 2 matrices. Each one has num rows, num columns, and it has a pointer to some set of data. All right. So in this case, the number of columns for this matrix is 3, and the number of rows is 3. And in the other one, the number of columns is 2, and the number of rows is 4. In each case, they are pointing to their own set of data. When we now say swap, what we're trying to say is we don't want to have to swap all the individual items. We know that this set of memory should now simply be associated with that matrix, and likewise the other way around. So this set of memory should be associated with that matrix. So this is fairly simple. We don't need to do too many complicated things. We simply need to say that. So this is now a fairly simple process. What we need to do is swap the integer values, and then we simply need to swap the pointer values to associate each object with a different set of allocated memory. So we keep some temporary space where we have an int star star. If this is A and this is B, we can now simply say that temp is equal to A.data. So we remember where the address of this green block is. We also then have to temporarily remember the number of rows and number of columns. At that point, we can now start to copy across the data from B, and we can simply say that the number of columns is 2, the number of rows is 4. At the same time, we can break this link in A, and we can say set it to point to the data from B. So at this point, they're both pointing to the same set of data. Following that, we can start to update matrix B. We can say we can update its number of columns to be 3, and we can get that because we remembered it down here. So we can update the number of columns and we can update the number of rows. Following that, we do the same thing with the data pointer that we did before. So we break the link that we had by simply setting it equal to that temporary variable where we saved the address earlier. The next function that I'd like to talk about is the copy matrix function. So there are two parts of this function that we need to think about. The first one is that it says that we need to return a pointer to a new matrix that contains a copy of the data in this one. So the first thing we do is we need to allocate space on the heap. So we have MyMatrix, and it's a pointer, and we allocate on the heap using the new keyword. We know that the constructor then takes in the number of rows and the number of columns. That will then set up all the memory that we need. Now at this point, we need to copy all the data across from the current matrix into this new one. So we do this by having a for loop. And in that for loop, we then need to set all the values in our out matrix. So because out is a pointer, we access its members using the arrow. So we say out, and we access data, and we want to change the value at ij, and we want to set those equal to the current matrix data at ij. And then following that, we would simply return out. Now, it's very important in this case that we do actually have two for loops that iterate over all our data. We can't simply say something similar to this. Now, it's very important in this case that we have the two for loops and iterate over all our data, copying it across into the new array. We can't simply say that out data is equal to our data. The reason for this is obvious if we go back to our swap function, where if we said a.data is equal to b.data, all it does is simply have both of them pointing to the same dynamically allocated memory. So in the same case, we would have said create our two matrices, our current one and the new one. So this is the layout that we have. If we simply said out.data is equal to data, all that would do is break this link over here and set that pointing to the same block of memory. This would mean that out and this are both referencing the same thing, and it means that if we change anything in this current matrix or in the out matrix, it changes the other one because they're both pointing to the same thing. On top of that, we now have a memory leak that says we can't access any of this data anymore. We don't remember where it is, we can't remember what its address is, and we haven't deleted it, which means that this will now sit on the heap until our program either crashes or when our program finishes and the operating system takes back that memory. So it's very important in this case that we stay away from adjusting pointers and that we make sure that we copy the actual data. So the next section that we need to look at is the function called MultMatrix, which we use for matrix multiplication. This function is supposed to return a pointer to a new matrix that contains the result of multiplying this and another matrix. The first thing we need to think about is what the size of this new matrix is going to be. If we have a 3 by 2 matrix, say 1, 2, 3, 4, 5, 6, and we multiply that by a 2 by 2 matrix, 1, 2, 3, 4. We know that the output size of this matrix will simply be the number of rows in the first matrix by the number of columns in the second one. So we know that our output matrix will be 3 by 2. Like that. So the first thing we can then do is allocate our new matrix. So we would say MyMatrix, and it's a pointer called out, is equal to a new matrix which will have the same number of rows as the current one and the same number of columns as the other one. Once we've done that, we now simply need to think about how to fill in all these values. So the next thing we need to do is think about what the values in the output matrix should be. So in general, the way that I find this the easiest is to pick a space in the output matrix. So in this case, we're talking about row 1, column 1, which means that we take the first row and the first column of the two matrices respectively. Following that, we say that the output value should simply be, in this case, 1 times 1 plus 2 times 3. And we see that we calculated that by saying it's A at row 1, column something, multiplied by B at row something, column 1. We then sum over all these rows and columns. And we know that those will be the same numbers because this is the only way that matrix multiplication works out, is if those two numbers are the same. So we can say for I equals 0 and I is less than the number of columns in A or the number of rows in B, which should be the same. I plus plus. And we can say that the output starts off at 0 and then we continuously add to it. And then from here, it's simply important that we do this for every possible row and column in our output matrix. And that will finally fill up our output matrix with all the relevant numbers. Now, there's just a small syntactic issue that in this case, rather than accessing our values of the matrices directly like that using square brackets, we would need to say a.data at whatever coordinates, and the same for b. And then because out is a pointer, we need to use the arrow. So out at data would equal something else. And that would allow us to do our matrix multiplication. Okay, so we spoke about two different ways of calculating the nth power of a matrix. So specifically we have a slow method, and that slow method is just the standard naive method that you would use. So if you wanted to calculate a to the 4, you would simply say a times a times a times a. So in this case, whenever we want to calculate a to the power of n, we end up having to do n minus 1 matrix multiplications. We came up with another method, which we just called the fast method, and what this method does is it takes advantage of the binary decomposition of a number. So if we're looking at a power that's equal to 5, we can take advantage of the fact that 5 is simply equal to 4 plus 1. So we can say that a to the power of 5 is equal to a to the power of 4 plus 1, which is equal to a to the power of 4 times a to the power of 1. Now, what's useful about this method and what makes it so powerful is that it's very quickly to get powers that are a power of 2. So for example, by saying a times a, we can get a to the 2. By saying a to the 2 times a to the 2, we can get a to the 4. By saying a to the 4 times a to the 4, we can get a to the 8, a to the 16, a to the 32. And we can get these, for example, by doing 1 multiplication, 2 multiplications, 3, 4, and 5. So what we see here is that the number of multiplications that are required in order to get to the power that we need is logarithmic in the power. So if the power is 32, then we simply need to do 5 multiplications. And that works out quite nicely as just log base 2 of n. Correct? So that works really well if the power that we need happens to be 2 to the power of something. If it's not 2 to the power of something, then we can still take advantage of this, and we use it just like we do with any normal binary number by making it up out of a number of different powers of 2. So we calculate these powers of 2 and we simply decide what they are that we need. So for example, if we use the number 9, we can simply say, in order to convert that to a binary number, we know that we would say 9 divided by 2 would give us 4, remainder 1. 4 divided by 2 gives us 2, remainder 0. 2 divided by 2 gives us 1, remainder 0. 1 divided by 2 gives us 0, remainder 1. So we know then that the binary number would be 1001, and that's the binary number for 9. And we see that if we were converting it back to decimal, we would be saying that's 1, 2, 4, and 8, and so we would see that this is simply 8 plus 1. Now when we're doing this as a power, we would be able to say that's going to be a to the 9 is equal to a to the 8 times a. And as we work our way down our list of powers of 2 that we see on the top right corner here, we can calculate those as we go. So the first one that we got told us that indeed we did need to use a to the power of 1. This 0 told us we didn't need to use a to the power of 2. The second 0 told us we didn't need to use a to the power of 4. And finally, the second one told us that we did need to use a to the power of 8. And so we can simply keep track of those as we go as our final total. And then once we get to the end, once we get a 0 and we know that we've completely represented our number in terms of binary, we're then able to say that we've calculated the final number. Okay, so I'd now like to do a more concrete example of the fast matrix multiplication. So we're going to take a matrix A equals 1, 2, 3, and 4. And we want to raise that to the power 6. So the first thing we do is we set up power. And we say that that's equal to A. With that as well, we have our output matrix, and that's equal to the identity. So we said that A was 1, 2, 3, and 4, and that the identity is 1, 1, and 0s everywhere else. We have that n is equal to 6, and so the first thing we do is divide it by 2. 6 divided by 2 gives us 3, remainder 0. Because that's a 0, we don't need to worry about a to the power of 1 being part of our decomposition. So we then square power, so we multiply it by itself, okay, and that takes us 1, 2, 3, 4, multiplied by itself gives us 7, 10, 15, 22. Once we've done that, we then divide n by 2 again. 3 divided by 2 gives us 1. Remainder 1. Because we've got a 1 as the remainder, we know that an a squared is part of our decomposition. So we would multiply this identity matrix by the a squared. We know that the identity times anything should give us 7, 10, 15, 22. We know that the identity times anything gives us that same matrix, so we get 7, 10, 15, and 22. Following that, we then need to divide, we need to square power again. So if we say a squared times a squared, that gives us a to the 4. And so in this case, we end up with 199, 290, 435, 634. We now say n divided by 2. 1 divided by 2 gives us 0, remainder 1. Because there is a remainder 1, we know that the current power must be part of our output. So we take our current output and we multiply it by that. So we're saying 7, 10, 15, 22 multiplied by 199, 290, 435, and 634. So in this case, that gets us 5743, 8370, 12555, and 18298. At this point, we see that n has reached 0, and so we know that we're finished. At the same time, if we look over here at our output, we see that it consists of an a squared multiplied by an a to the 4, which definitely gets us to 6, just as we'd expect. So we had 2 matrix multiplications as part of our exact output, and then we had a times a, which got us a squared. We then had a squared times a squared, which got us a to the 4. So we had 1, 2, 3, 4 matrix multiplications. If we used our naive method, we would have said a times a times a times a times a times a. All right, and so that would have left us with 1, 2, 3, 4, 5. So in this case, it saved us 1 matrix multiplication. That doesn't seem like a lot now, But if n starts to grow, we find that the naive method gets very slow very quickly, while this fast method performs very well even as n gets big. Once you've coded the function to multiply a matrix, squaring a matrix is easy, as you're just multiplying by itself. And so once you have those functions, this actually becomes very easy to do. Remember that you can calculate the remainder using the mod function. So n mod 2 equals 1 is the condition that we use to include curr power in our output. And you'll find that you'll be able to code this fast method in around 10 odd lines. So it's not very long. I hope that this video has helped you understand some of the things that weren't clear in the lab. If it's not clear, please speak to a tutor or come and see me at some point.